let's think about the two previous examples and what they're telling us. So for the first one, we computed that improper integral. It converged, and so my series converged. And this one, I computed the improper integral. It diverged, and my series diverged. So all we need to do is compute that improper integral, and it'll tell us if our series converges or diverges. And so that's what I'm going to call what's called the integral test. Okay? So this is kind of like the moral of the story from the past two examples is this thing called the integral test. So to use it, when we turn our series into a function, this function it needs to be a continuous, positive, and it needs to be decreasing on our interval 1 to infinity. So you have to check all of those things. In particular, you always need to check that the function is decreasing. Usually it's always continuous and positive. And I'm going to assume that when I plug an n into my function, I get the terms that are in my series. Then, two things. And these two things are exactly what we noticed in the two examples we just did. So the first one says if the improper integral is convergent, like it was in the first example, then the series is convergent. And the second thing is going to say if the improper integral is divergent, then the series also diverges. So this is great. This gives us another way of checking if a series converges or diverges. I just turn it into a function, make sure that that function is positive, continuous, and decreasing, compute the improper integral, and whatever happens with the improper integral is what happens with the series. They're a pair. They have to agree with each other. Okay?